When you spill a glass of water, the second the liquid hits the fabric, the impact zone turns a deep, saturated navy. But water itself is completely transparent. It carries no color, no pigment, and no dye. Adding a clear liquid to a colored shirt seems like it should have no effect on the brightness, yet the material immediately darkens. To find out why, we need to shrink down to the microscopic scale. Subscribe to the channel and let's go inside the threads. The answer lies at the structural boundary of the material, where the geometry of its fibers dictates exactly how light is permitted to escape. Under a microscope, fabric reveals a tangled web of thousands of individual cylindrical fibers, held apart by millions of tiny pockets of air. When light hits this jungle, it travels through air and strikes the dense cotton. This sharp transition forces light to ricochet backward immediately. The collision shatters the beam, scattering photons straight back to your eyes before they penetrate the thread. A bright-colored shirt is a surface that successfully rejects incoming light, forcing photons to bounce back to your retina before they can be absorbed. When water hits the shirt, capillary action sucks the liquid into the microscopic air gaps, aggressively evicting the air and taking its place. Every material has a refractive index, a measure of how much it slows down light. Air sits at roughly 1.0, while the fabric fibers are closer to 1.5. That specific mathematical gap between 1.0 and 1.5 acts like a wall, creating the high contrast scattering we see on a dry shirt. Water has a refractive index of 1.33, which effectively bridges the gap between the air and the cotton. This refractive index matching destroys the initial reflective barrier. Incoming photons can now slide deep into the wet fibers rather than being rejected at the surface. Follow a single photon that has now bypassed the outer layer and entered this water-saturated network. As the photon tries to escape, it hits the boundary where the dense fiber meets the surrounding water. Because light strikes this boundary at a sharp angle, it triggers total internal reflection, acting like a mirror. This reflection repeats endlessly. The wet yarn becomes a web of leaky fiber optic cables, guiding light deeper into the fabric's interior. Water transforms the surface of your clothing from a trampoline that repels light into a labyrinth that traps it. While the light is trapped in this maze, it repeatedly strikes the chemical dyes waiting inside the fabric. This follows the Beer-Lambert law, which states that the longer the physical path light travels through a material, the more of it will be absorbed. On a dry shirt, the light path is short because it escapes instantly. On a wet shirt, that path length is now exponentially longer as the photons ricochet through the labyrinth. Each impact allows the chemical dye to absorb the trapped photons, destroying them and converting their energy into microscopic amounts of heat. Physicists have mathematically modeled this exact probability. These equations confirm that as internal reflection increases, the probability of total absorption climbs, causing the albedo, the brightness, to drop. The wet stain is a microscopic site of photon annihilation, where light enters but never returns. When we return to the macroscopic world, that spilled water takes on a new meaning. That dark patch is a zone of missing photons. Because the light is being trapped and absorbed internally, the wet spot reflects significantly less light back to your retina than the dry fabric surrounding it. You can see this exact same mechanism in reverse using a simple piece of cloudy, frosted tape. Normally, the rough surface of the tape scatters light, appearing white and opaque. When a finger smears a drop of oil over it, the oil matches the tape's refractive index. The scattering disappears, and light passes straight through. We are removing the scattering boundary. Because the tape lacks colored dye to absorb the light, the result is transparency rather than a dark stain. This behavior applies to almost any porous material, including the sand on a beach, which turns a dark, muddy brown the second a wave hits it. It explains why pale concrete and asphalt drastically deepen in tone during a rainstorm. In each case, water displaces the air, matches the refractive index, and forces the material to swallow its own light. What everyday physical mystery should we decode next? Let me know in the comments. Complex physics is often hiding in plain sight, turning a humble piece of clothing into a localized zone of photon annihilation.